or a government committee. So what is the model? What does it predict? How accurate is it in plain terms? And what should decision makers do with it? Now, of course, you should also be prepared to answer questions that the policymaker may ask you. And we have some example questions in the notebook below. Okay. Now, in order to determine what it predicts and how accurate, we need to set a particular threshold. Now, this is our choice. This would probably be dependent on what the policymakers told us in advance was their target. Now, it's also possible to present a range of thresholds. You might give more than one alternative, but you should give at least one alternative for the policymaker to evaluate. All right. Here, when we set the threshold here, if you remember, the two important quantities are the precision and the recall, because these have practical importance. So from this threshold, you get a certain prediction, accuracy and recall. So if we look at the summary here, this brief summary does address all of the questions that were listed above. Okay? So the model, really, I suppose this part is less important for those who are non-mathematicians, but it is important for completeness to tell what kind of model you're using and what you trained it on. You don't want to go to a subcommittee and tell them, well, I just came up with this model out of my head. You need to show that you did do a modeling procedure and it is based on real data. Right? So what does it predict? The model estimates each child's probability of dying before their 5th birthday based on information available at or shortly after birth. Okay? And here we list some of the. Now, if you're going to be a formal presentation, you might make an entire slide based on this. You would give the actual factors, right? And you might give some graphs that show distributions, but you should give some idea. You should dedicate some of your time to what it predicts in simple terms. So how accurate is it? Okay. So here it says AUC ROC 74%. The model correctly ranks a randomly chosen. See, this is the interpretation. The model correctly ranks a randomly chosen high-risk child above a low-risk child 74% of the time. Okay. So that's something that the policymaker can understand. I think that the next issue is more intuitive. Here it actually tells you for a particular choice of threshold, the recall is 66% of children who die before age 5 are flagged. Right now, that's something a policymaker can understand. That means if they use this model to identify high-risk children, in fact, 66% of the children who actually are at risk of dying will actually be identified. Okay. So that's good. 2/3 of the children who do in fact die would be previously identified for possible intervention. But that does mean also that 1/3 of the children who die before age 5 would not have been identified by this study. Okay? So this study does have limited applicability. Okay? Now the precision says that 20% of flagged children truly have elevated risk. Now I think that this is made more precise down here. 3,946 of 11,551 children would be flagged. So here it says that this model, if applied, would flag 34% of children. That tells you the magnitude of the intervention effort that you would need to implement in order to apply this model at this threshold. If I want to identify 66% of the at-risk children, I need to flag 30% of the entire population, okay, which is a high cost. If you want to screen 34% of your population, that's a very high cost. What's the population of Nigeria? Several hundred million. 34% of several hundred million is a very large number. Okay? So you need to present this to the policymaker so that they can make decisions. They will probably say, we don't have enough money. So they say we don't have enough money, then you'll have to lower the threshold. Okay. You have to lower the threshold so that no, I think you have to raise the threshold. You would have to raise the threshold to reduce the number of children that are flagged. Okay, but at least this sets a benchmark. It sets a point of a target for policymakers to consider. Okay, so what should decision makers do? You should be very careful not to recommend more than what the data tells you. Okay. So in this, what the data tells me is that I should flag children above the threshold for priority, but do not deny services to unflagged children because many of the unflagged children are, in fact, at risk. Okay. All right, so this was for a particular threshold. You can set other thresholds as well. Okay. All right, so here, in this exercise, you can try a different threshold and see what the effect is. I do recommend that you do this exercise. Try a different threshold, see what the effect is. Okay. And then you could make a different recommendation. Okay. In fact, the solution is down here, that if you have a smaller threshold, then for instance, this threshold would give you very large recall. This is completely impractical. This means you would have to screen every single child, basically. Okay. If your threshold is 0.65, then your recall is 0.37. You would get 37%, but your precision is only 26%. In this case, you're only flagging 14.5%. So this means that the number of children you flag is much less, but the probability of catching the child at risk is also much less. Right? Okay. Okay. So let me pass by this. All right. So this tells you some implementation detail. It tells you what the costs are going to be and what benefit you can expect. Now, you can get more information from your study. Your study, remember, used features of the data, and based on these features, it made a prediction. Now, some of these features are more important or less important. It's good for the policymaker to know which is important. This is important because they might possibly address amelioration of these features. Okay. So there's a way of determining the importance of features in a general machine learning model. But there's more than one way, but the most common and the best way is called permutation importance. Okay. Now I won't go into the details of how this works. What it does is systematically remove the effect of one variable at a time. It takes all the variables, takes one variable at a time. It removes the effect of that variable, and then it recomputes the probabilities. And the reduction in accuracy reflects the importance of that feature. Okay, so you take the feature, you remove its effect, you find a new accuracy, and you compare that with the accuracy when you include the feature. So that tells you how important the feature is. Okay. Now, unfortunately, this does not address correlation between features, but it does tell you something about how the features are important. So if you do this on this data, you can see this list of features and their importance. And as good practice, we have error bars, which are these confidence intervals. So what does this mean? This means that wealth quintile has a you could say it has almost 3 times the effect of the next feature. And this number here tells you the AUC decrease. This is less important than the relative ranking of the different features. I mean, this is certainly telling you that this feature is much more important than these two, and then the importance rapidly decreases as I go down the features. So these are features that could possibly be targeted, right? So zone northeast is an important feature. What does that mean? Maybe efforts should be targeted at the northeast zone. Okay? Maybe screening should be targeted at northeast zone. Maybe the conditions of northeast zone should be further examined. That's what statistical studies do. They give you indications of further studies to do. There's no end of study, but it does tell you the direction that you should go. Okay, so certainly you have the 3
So regional equity system. So of course, there's a large demographic difference between different regions of Nigeria. So if the model performs worse in one region than another region, then that's the great disadvantage of the model. Then legislators from this region will complain, say your model is not good for our region. We should have a model that's equally good for our region as for other regions. In fact, we're just using one model for all regions. We could use a separate model for the different regions, and that's a possibility. If the models for different regions are very different,
then we should consider doing different models for different regions. But this is something we should check. Is our model fair? Is it going to treat different areas fairly? Okay. So you can actually compute the AUC for different regions. And let's see what we have here. All right, so we did this. So we did this before. We did this before. This is the same result we had before. We talked about recall at the different thresholds. Okay. Right. Okay. So, all right. Let's see. Let's go down and see the result here. So here you see the AUC by region. Okay. So what do you notice from these numbers? What do you notice from these numbers? Anybody? You need to be able to read numbers. Okay. Which is the worst performing model? Can you read the numbers there? They're very small. You can try to make them bigger. Okay, Northeast is the worst performing model. And which is the best? Southwest is the best performing. Okay, all right. So there's a cause for possible further investigation here. Now, I suspect that one reason why Northeast is performing worse is because the infant death rate is larger at Northeast. So it's more difficult to make the model accurate. I suspect that's one possible reason. But this is a cause for further investigation. You can see that this is quite a significant difference. 0.683 up to 0.768. That's close to 15%. So that really is a cause for further investigation. Okay. All right. Let me go up to these questions here. All right. Okay. All right. So look at this question here. The feature, so it's, well, as I said, it's important for you to be able to answer questions that people might ask you based on your study. So here's a possible episode that might happen. The feature importance chart in part 2 shows maternal education and wealth as top predictors. Remember, we showed this before. I just remind you where that was, right? Wealth and maternal education. These are the top 2 important features. So a journalist looks at your results and he says, the model says poor uneducated mothers have children who die. The government should improve education and reduce poverty. Well, this sounds, but what is wrong with this interpretation? This claim is not supported by the evidence. Right? It's important to think about this. This claim is not supported by the evidence. Why not? It's true that education and maternal and wealth are predictors. But does that mean that reducing them will reduce death rate? Okay. Okay. Well, the answer is no. The study only shows association. It does not show causation. Study only shows association. It does not show causation. For example, perhaps poor diet is a cause of infant death, right? Perhaps poor diet is the cause of infant death. Now, of course, people who have lower income will have worse diets, right? But if you just improve income and they still eat badly, then nothing happens. You see, you're addressing the wrong issue, right? There's almost that there's an association. There may be a causative factor that's associated both with poverty and with death. You see what I mean? Okay. Maternal education is related to, here it says maternal education is related to infant death. So they say improve education and it will be better. But it may be that in certain regions, the education level is less and the mortality is greater in that region for other reasons. Okay? So if you just blindly say that improving education will reduce infant death, then you're addressing the wrong issue. What this does indicate is why uneducated mothers have higher death rates. You should look into why poor families have higher death rates. You should not just assume that you can fix it by changing this. the same thing in medicine. You have symptoms, have causes, right? You have a disease, you get a fever, right? Okay. So how do you treat the symptom? You treat the symptom by putting water and cooling them down. Is that going to cure the disease? No, you treated the symptom. Okay. So there's a difference between symptoms and disease. This is saying that maternal education is a symptom. That doesn't mean it's a cause. Okay. All right, good. So I want to stop here. I do want to take some questions, but I want to limit the question time. Okay. So so now it's 1:24. We'll take 15 minutes for questions and then move on because I want to cover more material. Okay. So do you have questions about so I don't know if we can share the microphone or what. If you give me the microphone, I can share. Yeah. Yeah.
Or
All right, there's one over there.
one, 3 persons.
Okay,
All right.
that's good. 3 persons is enough. We'll just deal 3 questions, it's fine.
Yeah.
4, 4 questions, that's perfect.
Okay, so let me start from
4 questions is
Yeah.
perfect.
quickly.
Well done, Prof.
Thanks.
Please, I want to ask, at some point you use a precision recall AUC, ROC,
Yes.
but now I see you using AUC. So what's the difference? At what point do you use precision recall AUC and just AUC?
Okay.
So I want
Fine.
to know the difference.
All right, very good. So AUC gives you an overall picture. Okay. We are using AUC to decide our best model. Now, when you report to the policymaker doesn't understand AUC. So you need to give the policymaker something that they can understand. So at that point, you want to tell them precision recall. Now, they don't understand precision recall either. So you have to tell them in terms what precision and recall mean. You need to give them some example. Okay? So the short answer is use AUC to determine your model, and then use precision and recall to present your model. Okay.
Okay. Thank you, presentation. So as part of the beginning process, right? I'm talking about the at the point of splitting. So
Okay.
we have the validation set and the test,
Okay.
right?
Right.
And in session 4, you run the prediction on the validation set,
Yes.
and session 5, you run it on the actual test set.
Yes.
And it's still the exact same model that was used in the previous session. So it's more like you're trying to get a better performing model. Now, in session, I mean, that intermediate step is really necessary. I mean, you could just run them on the test data, right? And you get the same insight.
Now, the question is that, so you're saying that you can leave the training set? You don't need to do the training? As you just do everything on the test set? Is that what you're saying?
Yeah, because you selected the best performing model, right? Which is based on this particular study,
Okay.
XGBoost
Right.
from session
Right.
4,
Right.
and you just directly use it on the test data.
Yes, that's right.
Yeah. So my question is that, I mean, we've already decided completely on the best performing model in the session 4.
Right.
I mean, how about just instead of that stage, we run all the different models on the test data itself and just pick the better performing one.
Okay. All right. So the question is, why not use all the models on the test set? Okay. That's a very good question. And I think that is a possibility. That's not usually what's done. Now, you need to be very careful about bias. You do need to be very careful about bias. And, I think what I'm going to do is I want to think about that question more, and I can answer it better tomorrow. But that is not the way it's done. You certainly do need both training and testing. But the general philosophy is that you make all your decisions based on training, and then you see how it generalizes to data that you don't have already. So let me think about that, or I want to get a better answer for you, but that's a good question.
Yeah, thank you, Prof. So I'm looking at the policy implications of whatsoever we are using the machine learning to run.
Yeah.
Since we know that the wealth and the education is one of the more important factor in terms of predicting the debt, right?
No,
In this
no,
case,
that's wrong.
yes, there is
absolutely
an
wrong.
association, but not
Yes.
causality.
So you can't say it's a factor in preventing the death.
Okay.
It's a factor associated with the death.
Yes, associated.
Yes, okay. Be
Yes.
careful about your language. Okay. Be very careful about your language, please.
Yes. So exactly my question. So at what point can we say we have our data and want to actually show causality?
Okay.
Are we going to be doing something like multiple logistic regression or some other model, or what exactly can we use to answer these questions?
Okay.
To say, okay, now a causality in terms of this very factor. Looking at the policy effect, there is the Pareto effect to say, okay, if we have a list of 5, 10 factors that leads to infant mortality or under 5 mortality, for example, what are those ones that we need to take to the policymaker to say, okay, if you take care of these few items, it will have more impact in reducing.
Again,
Yeah.
you're doing the same mistake again. You're making the same mistake again, that you don't know that these factors are causative, so that you don't know to take care of them or not. You're just saying that they're associated.
Yes, I know, but the question I'm actually asking, is there any other way of asserting causality effects?
Yes, there are different techniques that we have not covered.
Okay, thank you.
But that's completely different, right? So it's completely different. I think that in some of the later notebooks, it talks about some of these techniques, but nothing that we've done, none of these statistics, and indeed most of machine learning does not tell you anything about causality. Okay, you have to do some other kind of study. So what you can say is that I can say roughly is that you need to control exactly for that variable. You need to find a set of people that are the same except for that factor. You understand that they're identically, demographically, they have all features the same except for that one factor. Okay? And then see if there's a difference. Okay? Then you're isolating actually the effect of that one factor. Okay, something like that. But we did not do that. We did not do that. Okay, so it's a good question. Thank you.
The final question.
Okay, good afternoon, Prof. So based on session 4 yesterday, we were making mention of classification, probability, and prediction outputs.
Yes.
So the question I want to ask now is because my brother actually asked that question to you yesterday, but you did not really understand him. So what we're trying to know is that when do we use classification in machine learning? And how do we know whether we need classification, probability estimates, and prediction outputs?
All right. Okay, so the difference between classification and prediction, I think that, what should I say? I think that this is determined on a case-by-case basis, all right? So in this case, it's clear we want to find high-risk children, right? So we want to distinguish high-risk children from non-high risk. So this is a clear classification problem. Now, on the other hand, if we want to predict malaria rates in the next month, a malaria rate is not yes or no. I mean, you can ask, will there be malaria next month? The answer is yes, of course, okay? But if you want to predict the rate, that's a prediction problem. You're not going to get a yes-no answer, right? Now, you can ask the question, will malaria rates next month be above 10%? That's a yes-no question. Okay? So the question determines whether it's classification or prediction. Okay. If it has a yes/no answer, then it's classification. If it doesn't have a yes/no answer, it has a numerical answer, that's prediction. Okay. All right, good. Well, thank you for the questions. Let's go on to notebook 6. Okay. Notebook 6 starts another study. Okay. In fact, it's the study of the same material, but it goes into more detail. Right. So again, so there are various details for examining features, examining their importance, examining their effect on the model. Okay. So here again, I'll just scroll through this, and you can see some of the aspects. So again, we check what's installed. Let me do my other version here. I'm going to do this one here. Oh, I don't have it. Okay, so let me just open that. Okay. All right, so we install missing packages. Okay, okay. So advanced model building. Now, one thing cross-validation to determine the parameters, and one level to determine the model. Okay? That's called nested cross-validation. And scikit-learn does that for you. It has a package for that. Okay? Right. And then you want to fit the tune model finally and synthesize. Okay. All right. Okay. So the big question is, the hyperparameter optimization, is there a smarter search? Then the answer is yes. So we use the notebook the same way that we've used notebooks before. We use the same data as before. Now, this reloads from scratch, so it will simply do everything that it did before. Okay. Okay. So in sessions 3 through 5, we compared 3 models: logistic regression, random forest, and XGBoost. And we picked a winner mostly on accuracy. Starting today, we treat that winning approach as a research grade project, not just building a model, but tuning it properly, explaining its prediction, and auditing it for fairness. Okay? Okay. So we've mentioned that all of these are important. Okay. That we want to tune, we want to explain, and we want to make sure that it's fair. So this is a more thorough treatment of these 3 issues. So in this session, you'll use a different parameter optimization. You'll compare this new model, Light GVM. You'll implement nested cross-validation to reduce the bias on performance estimate, and then you understand optimism bias. Okay. So just forget about this note. This is out of date. So these cells should be familiar to you by now because this is the same cell we've had in previous notebooks. We've had this same is the same. So again, I recommend you set this as true. You load the data and you rebuild it and you redo everything we did before because we want to regenerate our model. So we're doing this on the 3 different models that we had before. Right. So here's the let's see. So we have this. So this is to prepare the data. We use that for all of the models. We do the train test split. We use the same train test split on all the models. In trees that we talked about before, every tree has a level. We know, for instance, that the depth of a tree. So let me just like if I just explain this a little bit. So, for instance, what does this mean, tree growth? I'm going to explain this a little bit. What does tree growth mean? Now, for XGBoost, we've seen XGBoost uses acidity. XGBoost uses
Right? Each decision is based on a criteria, and each decision has two daughters. So it goes down like this. Right? So this has three levels, and what's the depth of this? It's two. Right? What's the relationship between the number of levels and the depth? You see the relationship between the number of levels and the depth? You've got three levels, 1, 2, 3, and your depth is 2. The depth is 2 because you have two decisions. Which one is bigger, the level or the number of decisions? There's two decisions and 3 levels. Right? 1, 2, 3 levels and 2 decisions. In fact, the number of levels is always one more than the number of decisions. Right? Because you start at a level even before you've made any decision. So the number of levels is always one more than the number of decisions. So this is actually goes through this tree like this. Conventional trees that have levels. So you have levels. And the nth level has how many leaves? Actually, these are what we call leaves. Or these are what we call leaves. I should say a tree with 10 levels has how many leaves?
Just present the table. Just present the
You
table.
need to know a little bit of that.
Okay. Okay, this is one, this is 1, this is 2, this is 4, right? How do you get 4? 4 is 2 times 2, right? How many 2's do I have? 2 times 2. That's right. 2, how many are there? There's 2 here. But in fact, if I have n levels, I will have 2 to the n minus 1. Right? Here I have 3 levels and 4 leaves. Right? So in this case, that's the relationship between leaves and levels. So, but like GBM, is leaf-based. So what does that mean? In light GBM, the tree looks different. Okay, the first decision may be like this, but the second decision may just have 1 leaf. Right? Maybe this category is not big. So actually, it would never have just one leaf. It may just stop. Okay, maybe this one has no daughters. If this category is small, then this one might have 2 leaves. Right? And maybe this one is small enough, so and this might go on like this. Okay. Like this. So what does that mean? That means that your tree can be deeper with fewer decisions. It's the decisions that cause time to train. And it's the depth that allows you to have a descriptive model. So light GBM allows you more leaves and less, allows you more depth with less decisions. More depth, less decisions. Or less, yes, that's right. All right, so it's much more flexible and it does perform. Okay. So that's the basic idea. So you can see that that's why it's much faster on large data, okay, and uses less memory. Okay. All right, so you can also optimize the parameters for light GBM. Right. So I think that this is kind of the discussion here. Leaf-wise level-wise growth expands every leaf at the current depth before going deeper, a full balanced layer at a time. Leaf-wise growth, which is Light GBM's default, always splits whichever single leaf reduces loss the most, regardless of depth. So the tree can grow very deep very quickly. Okay, so given that description, why might leaf-wise growth reach a lower training loss in fewer splits than level-wise growth? And why might that same property make it easier to overfit on a smaller data set than the 65,000 row training set used here? Well, you can give some answer. I would say basically that Light GBM is more flexible and splits according to the data rather than always splitting the same way. So you can think about these questions. All right. So again, nested cross-validation. You can't use the same data both to select hyperparameters and to evaluate. You need two levels of optimism. So so nested cross-validation uses two loops, the outer loop and the inner loop. So the outer loop doesn't change hyperparameters, and the inner loop determines the hyperparameter. Okay. So I think that's in practice, that's what you need to know. That's why you use nested cross-validation, and you ask scikit-learn to do the implementation for you. All right. So this one here is the simple cross-validation without nesting. And then here we have here we have the XGBoost. And okay. All right. So run these codes, look at the plots they create, and then you try to understand the issues, and we can have more question and answer after you've run the code. I do want to do one more notebook before we get to. Okay, this one is talking about, I'm sorry, is this the right one? Yes, this is the right one. Okay, this one talks more about feature importance and how you can identify the importance of features for different models, not just logistic regression. So I've run this one and gotten output so you can see what it looks like. Okay. So there are various plots that you can use to determine feature importance and characterize it. There's something called a B-swarm plot. There's a waterfall plot. There's a SHAP dependence plot, and there's a partial dependence plot. Okay. So these are 4 different ways to represent your results. And let me talk about these briefly, and we can go into them more deeply next time. Okay. So what is a B-swarm? So first of all, what are SHAP values? SHAP values are a way to obtain feature importance without using for other models besides logistic regression. All right, so we go through all of these. That's not supposed to be there. Okay, so we go through all of these figures. So again, we reload the data. Again, we do the same thing. We use the same model. So all of this is repeat. We're refitting XGBoost because we want to use these graphs on XGBoost. Okay. Okay. What are SHAP values? Okay. So let's read this carefully and then try to analyze. SHAP values are Shapley additive explanations. Assign each feature a contribution to each prediction. Okay. Now, previously we had feature importance, but this is telling me for one particular prediction, how much did each feature matter for that particular prediction. So the difference between SHAP values, Titian importance, is that SHAP values are calculated individual by individual. Permutation importance evaluates the feature on the entire data set. Okay, so how do you compute SHAP value? SHAP value JI is the average marginal contribution of feature J to the prediction for observation I, averaged across all orderings in which features could be added to the model. Okay, now this takes some time to understand this. The actual mechanics of SHAP values are not easy to understand. What you do want to understand is that the SHAP value of a feature is telling you how important that feature is to the predictions for a particular individual. Okay. All right, so we don't really need to talk about the properties of SHAP values. You just need to know at this point the use of SHAP values. Okay. So let's get our SHAP value. Now, I thought I ran this. Let me run it again. I thought I ran these all. Let me run it again just to make sure that, so that we can discuss the outputs. Let me make sure displaying all of my graphs. Oh, this one, okay. I guess looks like I didn't do this. Okay. So we'll run this, we'll run all the graphs, and then we'll take a look at this. I don't think it will take too long. Let's see where we are. It may take a little while. Okay, well, while I'm running this, why don't I go back briefly to session 6 and see if you have any questions about this. Remember that in session 6 we talked about mostly about the difference between LGBM and XGBoost, and we also talked about nested cross validation for hyperparameter tuning. So again, let's take a few minutes for questions while my other notebook is running. If you have any questions at all on the material, let me know. But there's no sense just waiting while it runs. Let's just take some questions and have some discussion. So any questions? Okay, there's one over there. Okay. Okay.
So let's start from,
That should be good.
let's start from here, from number 3.
Yeah.
Okay, online. All right. So
Thank you, Prof. So I'm going to use a practical example based on the university. As now, I wrote a question here and I said, supposing a university want to predict which students are likely to fail a course. For instance, maybe they are doing MTH 101 and the university want to predict which students are likely to fail a course, assignment course, and the engagement data. Now, this model that you are saying, XGBoost, how is it going to help? And why might it perform better than a simple linear regression model?
Okay. What model are you referring to? Is that in one of the notebooks?
Yeah, this session, or when you're talking about XGBoost. So I'm asking that if they are going to predict universities and they want to use XGBoost, that's like, how will it be better than the other models?
Okay. So I'm sorry, is that in, which notebook is that in?
Session so-called XGBoost.
Okay, all right.
Yeah.
Sorry. So you say it talks about, you know about where it is? You're saying that it's predicting,
Yeah, a practical example.
give me some text to search for.
Yes. XGBoost.
Okay.
Yeah.
Well, there's a lot of XGBoost, but we can look for this. Okay. Boost, sorry. So that's book. Okay. Tell me where, when I get there.
Like- You not get it. You know, you were teaching us about XGBoost recently now, telling us the difference. So me, I'm giving a practical example.
Oh, you're giving
of-
another example. Okay.
Yeah, I'm giving an example of when I'm going to use XGBoost.
Okay. All right. Well, I think that when you use the model that you use really depends on the nature of the features that you're using to predict it. If you only have some very simple features, if you only have one or two features, there's really no need to use XGBoost. But if you have some features that have some complicated relationship, then you may want to use XGBoost.
Like for example, here as example, if they want to predict like which course a student is likely going to fail, can they apply this model for it?
Okay, so what features do you have?
The feature is going to have their attendance, their CA, their practical scores, and their engagement data.
Okay. All right. If you just have those 4 features, I think that probably XGBoost is not going to help you. XGBoost, that really basically the complication of the model determines the complication. The complication of the data determines the complication of the model.
All right. Question number 2.
The question is from one of the online participants,
Okay.
and the person is asking which machine learning model can be used to model causation, or how do we capture causation in machine learning models? And maybe when you're done, we have another question.
Okay. Well, I did address that already. The answer is that it's not the machine learning model itself that addresses causation. All machine learning models do the same thing. They will either classify or predict, and it will not tell you one thing is prior to another one. So you need to use some techniques on top of machine learning in order to get causation.
All right, sir. So the second question, Professor, regarding gradient boosting methods such as XGBoost and LightGBM,
Yes.
how important is the choice of 3 growth level-wise versus leaf-wise for modeling complex nonlinear interactions in clinical and epidemiological data?
Okay.
In particular, could the more aggressive leaf-wise optimization used by LightGBM increase the risk of fitting when the data set is relatively small or contains rare clinical outcomes?
Okay. Yeah. Well, I think that the answer to that is because LightGBM is more flexible, then it is easier to overfit. So you need to be careful about that. But there are things that you can do to avoid overfitting. Right? If you carefully arrange your test set and validation set, if your data is overfitting on your if your data is overfitting on your training set, then it will show up on your validation set. So that's the whole point of this process: training, validation, and testing. This is to guard against overfitting. It's to guarantee that you don't underfit, and it's to guard against overfitting. Okay, so I would say the answer: how do you prevent LightGBM from overfitting with small data? Is just apply the techniques well. Apply the techniques of training, validation, and testing well, and that will catch the model when it is overfitting. Okay. Another question over there?
Thank you, Prof. My question is more on your previous presentation.
Sure.
Yeah, where you tried to talk about how we can present our research data to policymakers.
Yes.
Yeah, so what kind of struck me, remember, was when you presented the data and you presented the threshold and you had results, but you kind of also said that the threshold can be adjusted and that will bring different outcomes. So my concern with that is if you are presenting, data to policymakers, to politicians,
Yes.
for instance, and you give them that hint that it has some activity to it,
Yes.
they might decide to exploit that and tell you, this thing is is not to my taste. I want it this way. Can you tweak it? So it removes the activity to statistics, to my modeling and stuff. So what's your take on this situation? Thank you.
Well, I think, I mean, the job of politicians is to make decisions, right? That's the job of politicians. So it's not your job to make the decision for the policymaker. It's your job to give the policymaker the information they need to make a good decision. Okay. So so I think the way you present this is you say, you tell the policymaker, what's your target? If this is your target, this is the result. If this is your target, this is the result. Now, if they tell you beforehand what the target is, then you can present the result, right? If they say, well, my survey size, my effort size, I'm only have enough resources to screen 10 million children. Okay. If I know that, then I can give them a number. Okay. If you screen 10 million, you'll only catch 15% of those at risk, right? So if they give you a target, you can give them a number. If they don't give you a target, you should tell them, well, for this target, you get this result. For this target, you get this result, right? Right? It's just a matter of communication. You want to communicate all the information that you receive. You want to communicate the information they want, but you don't want to over-present or under-present what your model shows. Okay. All right, good. Let's see if it finished running. And how much time do I have? Oh, half an hour. Okay. See if it finished running. Looks like it did. Okay. All right. So this is familiar. What we're doing here is we're looking at these Shapley values. The Shapley values are telling me the feature importance for individuals in the data set. Okay. All right. So this is more technical things. I want to get down to where it gives the graphs. And you can read this, you can read some of the details at home. All right, so I mentioned this also, what Shapley values are. And there's the different types of graphs. All right. Okay. So let me pass this one. Okay. All right, so first the B-swarm plot. Okay. So I'll show you a B-swarm plot, and it is a little bit daunting here. Okay. So what is this showing? Now, this is the same study that we had before. This is, again, infant mortality, and you're predicting infant mortality. And this is isolating the different figures, the different features. Total children is basically family size, and then household size, number of people in the household, and then birth interval, and then so on. These are all different features, and it's isolating the effect of each one. Now, each dot represents an individual in the sample. So each dot represents one child. Okay. So this what they call B-swarm is representing the effect of this feature prediction. Okay, so what this is saying is that total children, for instance, for this particular child, the total children feature had a large positive effect on the value. Now remember, the higher the value involves risk, right? So this means that this individual, the total variable had a high effect and tended to increase the risk estimated for that child. Okay, so for each child, the effect of this variable is different. Why is that? Because the different variables have interrelation. Sometimes total children may have a bigger effect on the prediction for one child than for another child. And so the effect of this variable changes from child to child. Okay? So this is telling me for this particular child, the effect was positive. Okay? And then, so you can see this here. No, I'm sorry. All right. So now for this particular child, also the feature value was very high. Okay. So the color tells me the value of the feature, and the position tells me the influence on my risk estimation. Okay. Color tells me the value of the feature, and position tells me the effect on the risk estimation. So what this is telling me is that children who have a high value of the total children tended to have an increase in their estimated risk. So you can see that that's consistent. You have the red associated with high values and the blue associated with low value. Now here it's somewhat mixed. There's a mixture of effects. Okay. So in here the value is near the mean. This vertical line is the mean of the values. So that's the SHAP value. Okay. So this had a net negative effect. This had a net positive effect. Okay. So that's where this comes in. Right. Now it's interesting here that sometimes, for instance, in this case, in this SHAP value graph, these have a low feature value. They have very low wealth, but the low wealth also had a negative impact on the risk. Okay. Now, typically, a high wealth is going to have a negative value, a negative impact on the risk. But for these two individuals here, the fact that they had low wealth had a negative impact on their risk that was calculated. Now, this is because they're, like in a forest model, they're trees and they're leaves. So this was probably for a very small leaf that included just a few samples. Okay? So you do get these kinds of outliers. This one is also quite interesting. That multiple Earth had most of them are clustered here, and then a few are up here. So these are the ones that had say twins and triplets. Now there's a few where the multiple birth the estimated risk. So that would be interesting to look into. That's the B-swarm plot. Okay. So it takes some time. That one dot is one child. The dot here okay. So if I pick out one child, so this is one particular child. Okay. Now I'm not sure why it's doing that. Okay. So this one had very high predicted risk, 76.4%. Okay. And you can see what the effect of the different features had on this. Okay. It turns out that for this child, the total children value, the total children in his family had a large effect on the estimated risk. The zone had a large effect. Household size, in this case, had a negative effect. So we can isolate the effects of each different feature on the risk estimated for this child. Okay, some had positive effect, some had negative effect. Okay. And so you can see which ones were most. Now we found previously that education was in general the most important feature in terms of the permutation feature important. But for this particular child, the education did not have a big influence on the prediction. That's probably because the education was typical. The education is typical, then it's not going to influence education on this particular child's risk. Right. Right. So in fact, this one here was a child who did die and had very high predicted risk. So in the exercise, you can choose another child who didn't die and see how their predicted risk depended on the different features. Okay. All right. So this next kind of plot called SHAP dependence plot. Okay. So a dependence plot shows how SHAP value for one feature varies with all value colored by a second feature. So this reveals interaction. Okay. The importance of one feature may depend on another feature. This is the idea of correlation, that different features are related to each other. Okay. So you can see this plot. For one of these lines, wealth is fixed. This is the B-swarm plot, but it fixes features one at a time. All right, this one says wealth is 2.0, and then it gives me the Shapley value related to the education level for that particular feature. So I could call this a B-swarm plot. It's a conditional B-swarm plot. It's conditioned on the value of a different feature. It's the B-swarm plot for wealth, but it's conditioned on a different feature. Okay. So this does give you good information. Okay. Last type of plot is the partial dependence plot. Okay, an ICE curve. Okay. What's a partial dependence plot? Partial dependence plot says the average predicted risk as a function of one feature marginalized over all others. So it's a global summary. So you're trying to see if the value of value of one feature changes, how does that change the average predicted risk? Now, this is going to change from child to child. Okay. If I just look at one particular child and see how their risk changes as the feature varied, then I get a more detailed picture of how this variable, how this feature influences the risk that's calculated. So let's look at this. Okay, so here's the ICE curve here. This one here, the dotted one. And what this is telling me is that over the that
All right, so we have come to the end of this session. Can go for a lunch break. The lunch break will last for 30 minutes. So by 3:30, we'll resume for the last session. We'll continue with R, which will be taken by Mr. Samuel Oshikoya. So we can go for our lunch break now. Thank you.